recorded a lecture, and here are all my notes. And then when I went to check that it was there, it was gone. But the bottom line is, maybe this is going to take 25 minutes or something, and I'm going to end class, and I will have this other part recorded, and hopefully sometime tomorrow morning you'll be able to find it and watch it before our next class on Wednesday. So is that understandable to everyone?
Yep, sounds good.
Yep. Okay. All right. All right, so this is an extended surface with surface heat flux. So we're going to try this example problem, and the idea is that I have this solar collector plate, and we're looking at it two-dimensionally. Let's say it comes out of the page very far, and it is supplied with a heat flux. And so this is a little bit different because our fins, we always assume we've got convection. We didn't even consider radiation. And in this case, this solar collector, we have radiation coming to the surface. We don't have any convection going on. And what they did is, and this is not uncommon, that we're going to evacuate, so draw a vacuum on this space. So we got radiation coming in. It comes through this transparent cover, and then there is a vacuum drawn between the cover plate and the absorber plate. So I should read through. So it says, copper tubing is joined to the absorber plate of a flat plate solar collector. So here's the copper tubing at these uniform spacing. The aluminum alloy absorber plate is 6 millimeters thick and well insulated on the bottom surface. So they're showing dots on the bottom that you're thinking are perfectly insulated. The tubes are spaced 0.2 meters from each other. Water is circulated in the tubes and can be assumed to be at a uniform temperature of 60 degrees C. For steady state conditions, the net radiation heat flux to the surface is 800 watts per meter squared. And they ask us to do two things: find the maximum temperature of the plate, and B, the heat transfer per unit length of the tube. So again, we're imagining I'm heating up this top surface of the plate, and then this plate gets heated up, and it gets heated up above 60 degrees, and it's going to transfer its heat to those tubes. So this would be a thermal solar collector. So our goal is to produce hot water in this case. Okay, I don't know what you guys think about this green pen color. I always find green is a little bit obnoxious, but since I'm doing just a shorter version for right now, let's go with it. Steady state, one-dimensional X direction conduction only, and I want to look at my picture. Yeah, I'm going to set an X coordinate right on one of these tubes, and this will be my X direction, so along the plate. And again, I maybe repeat this too often, but we're imagining that at a certain location in the plate, so a certain X location, the temperature is a single value. It doesn't if I think of this as the Y direction, it doesn't vary in the Y direction. It's a thin plate, it's metal. We're not losing heat from the top. We talked about it. It's an evacuated space. And we're not losing any heat from the bottom because it's insulated. And 4 is we're going to assume that the temperature of the plate, just where it touches the water tube, is the temperature of the water, which is 60 degrees. If you are thinking about this relative to a fin, you might think of this as the base temperature. So it's attached to this water source that keeps being, keeps flowing past, and it's at this constant temperature. And it can pull out as much heat as this absorber plate collects and still maintain its temperature of nearly 60 degrees. In this picture, there are some lines of symmetry. So I want to just look at a chunk. If this was L/2, let's consider that portion because heat that is absorbed on this section is going to go to that tube. And if I'm on this side of that halfway mark, this heat's going to go to this next tube. Okay, so it's like a line of symmetry or an adiabat. And I'm going to draw just a chunk of this tube, or this plate. Okay, so here's our plus x, and I'm making x equal to 0 right at the tube. Okay, and x is moving to the right. And then I've got this section of the and I want to sketch okay, and I'll do it in this direction. Then I have qx coming in, and I have qx plus dx in that little element of the absorber plate. And then on this top face, I've got radiation. And this is a little chunk of the plate, a little dx chunk. Again, so we got conduction through the plate, and it eventually gets delivered to the water tube. And I've got solar radiation hit the top surface of the plate. We are going to write an energy balance for that little element. So maybe I should hit this find again. It says the maximum temperature of the plate as the first thing. So the idea is we're going to set up a temperature distribution for the plate. And so we're starting with this energy balance. We're going to put Fourier's law in. We're going to come up with temperature as a function of x. And then we'll think about where we expect to see the maximum temperature and plug that location into our temperature distribution and come up with the maximum temperature. And just because I mentioned it, hopefully you're thinking, this is my line of symmetry. And let's use a different color because I've written too many times. Purple. That's my line of symmetry between these two tubes. And I know that this has got to be at 60 degrees because we said that's our assumption. And so to me, it seems likely that my highest temperature is going to happen right here, where I have this center line and I'm conducting heat away to this cooler temperature. All right, but we'll hit that again when we go to solve for the maximum temperature. So these two terms I've written really just symbolically so far. This Qx and Qx plus dx, those are the conduction in and out of that little element. Radiation, since it's a flux, I need to think about what I want to put in here. So I got this huge, we didn't say the depth of the plate into the page, but I'm going to call that W. And then my little element dx, that gives me the top surface area of the plate. Let's say this is depth into page. And those are the only things acting on this, and it's steady state, so they have to sum to 0. We have evaluated terms like this before over these differential elements, so I don't intend to go through all of the details of that. But just for example, let's think about Qx. And first of all, I've just written down Fourier's law of conduction. So I know my conduction is in the x direction. And then I really have to think about what the cross-sectional area is. And we've got this thickness given in this figure, thickness, and then that W, the depth into the page, gives me the cross-sectional area that I have conduction occurring through in this x direction. Okay. All right. So the difference in Qx and Qx plus dx gives me this term. And then I'm adding on my radiation. And I can cancel dx from both sides. Since we have constant properties, I'm going to take k out in front. The thickness doesn't change with x direction. The width doesn't change. So all of those things can come out front. And And then I want to divide through. Oh, we got W's canceling on both sides. Okay. I have dropped my radiation for this double prime term, but I hope you're remembering that's the radiative flux that they gave us on this solar panel. This is maybe looking like stuff you've done before, that we're going to integrate this twice with respect to x to come up with our temperature distribution. Then we have to come up with two boundary conditions to apply. To solve for those two constants. Okay. Just for a little interaction, anybody have an idea of a boundary condition we're going to use?
The 60-degree interface temperature.
Say that again. The 60-degree interface temperature?
The 60-degree temperature at the interface.
Yeah. Okay, right. So right where it's sitting above the tube. Yes. Okay, and we set our coordinate system that was going to be at x equals 0. All right. And hopefully I've made my picture. Okay, so this is, all right. And then the other one we're going to apply is that this line of symmetry at x equals L over 2 is an adiabatic boundary condition. And it turns out the adiabatic boundary condition makes one of the constants drop out, so it's a little bit easier to apply that one first. Okay, so again, this is that we had that line of symmetry, which behaves like an adiabatic line. I didn't show my intermediate step of this integration, so maybe it takes a minute to figure out where this equation came from. Okay. So if I integrated starting from this one, so if I took the derivative of this one to get dt dx, okay, and then I substituted in that x was equal to L over 2. Oh, wait. I'm sorry. I was thinking one of these goes away. This does not go away. This does not go away. But we can pretty easily rearrange this and figure out that C1 is equal to the heat flux times L over 2 kT. All right, now I feel bad because I was saying this is the better one to apply first, and I'm not necessarily sure that it is. It doesn't make our life way easier. Okay, so I'm putting in here that we know at x equals 0 that we're at the temperature of the water, that 60-degree temperature. And then I look at my equation. We can kind of get it up on the screen. So I'm putting in an x equals 0 here. Yeah, actually, I like your idea better. This one came up nice. So this says C2 is equal to temperature of the water. Okay. So now I'm going to substitute these constants into my equation and maybe do a little bit of rearranging. All right, so there was my, yeah, that makes sense. So that was my C1, and it was a function of x. And I am going to tidy it up maybe a little bit. We talked about this earlier when we set this up, but if I have this plate and I have tubes, and I know I got a temperature of 60 happening at each of these tubes, okay, and I'm applying a uniform heat flux, that we would expect the highest temperature is going to happen the way we set this coordinate system at L/2. So I'm going to have 60, something higher, flattens out and drops back down to 60 as my temperature distribution. So maximum temperature occurs at x equals L/2. So there's some simplification to be made to this. I think everything is given in this problem. We know radiative heat flux is 800 watts per meter squared. We know thermal conductivity. The thickness is 6 millimeters. We get a maximum temperature of 63.7 degrees C. Oh, and L, that was 0.2 meter separation between tubes. Okay. I think it's kind of interesting to think about. I mean, it's not a super big tube separation, but that's not much of a temperature. So I got 60 over here, and I got 63.7. So not a huge temperature change.
Quick question.
Yes.
So I know the book goes over how Tmax is at the insulated part of the material, but
At this line of symmetry,
right, which we treat as insulation. But
yeah.
how can we exactly make that assumption here that because we don't know anything about we know that there's radiation coming in, but how would we be able to assume that that center temperature is going to be actually the hottest point? What if like where we have the 60 degrees, if that's actually hotter than what we're like the energy that's coming in? How can we make that assumption?
Okay. All right. So we're picturing I got uniform heat flux over this whole surface. And we imagine we are keeping, I mean, this is one of the assumptions. I'm keeping this whole at x equals 0. I'm keeping this at 60 degrees. So we already know 60 degrees here.
Is it kind of like normally I guess it would be kind of a static problem where we would kind of assume that it's all this distribution is kind of concentrated at one point, and that point is the center?
Distribution is, I know, I'm trying to think of a way, mathematically, I mean, I can think of some things. We know I have to be driving heat that direction and heat this direction. Because I know I'm maintaining this surface at 60, this thing has to be heating up the whole, the solar absorber plate. So I
I don't
the
know.
water was heating the plate.
Yeah, I thought that's what Otto was getting at. Sorry,
Yeah,
we don't have to
okay.
stick on this more.
Okay, well, I'm going to say, I think maybe you're thinking 60 degrees C sounds warm, but we've got heat coming in. We've got heat, continually coming in. It's heating up the plate. It's got to go someplace. So even if that 60 degrees C sounds hot, we have heated the plate up above so that we are dumping heat into that water. So the heat's going into the water.
Understood. Thank you.
Okay. Okay, the last thing they ask for is to solve for the heat per unit length of tube. So one way to do it, I mean, this would be the energy balance way, is I'm imagining this. Let's do 2 tubes again, 2 tubes. This is my line of symmetry. All the heat flux that came in on this part of the absorber plate has to go into this tube. So if I just summed up the radiation times, and we're talking about the depth of the page, and then I want an L over 2, right? That's this distance. Okay, so that gives me an area. And then I got 2 sections. So this one tube really has another half of the absorber plate that it's collecting heat from. Let's see, the tube separation was 0.2 meters. Okay, and I still got this pesky W, but then I'm going to tell you but they ask for heat transfer per tube per unit depth. So I really just divide through. Ooh. All right, and I'm sorry about that. So that was a watt per meter squared, but this has really got a length unit associated with it. So if I was at multiplying through by this W, I've got a watt. Yeah, no, I am messed up. Let me think about this again. So we did 800 watts per meter squared, and we were going to have a unit of watt. So this gave me, this would have a unit of length. Okay. So the fact that I divided through, this gave me a watt per meter. Let's get rid of this row.
So that second row should just be 160 watts per meter. Right?
Watt per meter, yeah.
Times width.
So I want Q prime, and it's going to be Q double prime times L. I divided through by the per unit depth into the page, and it's 160 watts per meter. Okay, so the way that, I like that way, that's thinking through, and I promise I'll just show you this one more. Okay, I'm getting there. I'm getting there. All right. Do you remember, this reminds me of the fin. So this says if I calculate, here's my water tube down here. If I calculate how much heat is conducting through this x equals 0 location, that's the amount of heat that, it's actually half of the heat that the tube is collecting. So I can take the derivative of that temperature distribution that we calculated earlier, and this needs to be KAC, cross-sectional area. And I need a 2 in here because this is only going to give me 1/2, and I really have another half of the plate. All right, so I'm handling that. I've got 2 faces. I got a K. My cross-sectional area would be W, so the depth into the page, and a T. And I'm going to put my T over here, and I'll put Q tube per W, and not even carry that guy along. And then we got to do our dt dx. And I've already evaluated at x equals 0. And if I cancel things out, I got this pesky minus sign, but I think that's okay. I get back to the same result we had above, that it's the heat flux times the separation of the tubes, which we'd expect.
The minus sign is just because he's leaving the system, right?
So the heat is leaving and going into the water tube. In Fourier's law of conduction, we always put that negative sign in there, but I made my x going positive in this direction, and it's really, the temperature is decreasing the other direction. So I should account for my, always putting this negative sign for Fourier's. It tries to help you out with the direction of heat flow. But my dt dx, I didn't necessarily follow that negative sign, the direction properly.
Okay, so it's just negative because it's moving to the left, and we made our x positive to the right?
Yes.
Gotcha.
Yes. And here, all I looked up here in our first method is I just did a balance. And I knew whatever is absorbed went into the water. And then the second one, we did Fourier's law, and it assumed a direction. Okay. So again, this is the next part of the problem, and this is a moving fin. It's like an extrusion. So we have this thin filament, and my plan was, because this gets kind of late and kind of long, that I was going to record this lecture. I didn't get it finished, but I will do that early tomorrow and post it, and you'll just need to watch it before we meet next Wednesday. And you know that Monday is fall break for U of L, so we won't have a Monday meeting. Oh, okay. My plan is, and I didn't give you my motivation why we did that previous problem. It's like a fin problem, except I kind of like the fact that we didn't have convection occurring. Now we had a heat flux. And so you got to see this, setting up a differential element. We got a lot of features that were like, some things we've seen before. Okay. I'm hanging on for a few minutes, maybe till 6, and see if anybody has questions. Otherwise,
on that last one, where did the 2 go between the last step and the final answer?
In this very last part?
Yeah, right there.
Okay, so where did the 2 go?
I'm just now seeing the 2 in the denominator of the other I totally missed that in writing my notes down.
Oh, okay.
That's what it is.
Okay.
Yeah.
Yeah, I didn't show all. You have to take the derivative of that gradient.
Yeah, I copied it down wrong and was totally lost.
Okay.
Towards the beginning of this problem, right under the heading where you said putting terms into energy balance, can you go over that part really quick? Right there.
Okay. What do you-
Yeah, I got a
Um,
little lost on how you have like the d over dx times like the qx quantity and then another dx.
Okay. And I think the part is that I didn't show this. So we would write it as and then we have d by dx of this whole thing.
Okay, I think that's what I was missing.
Yeah, and so this guy cancels with this one, and we're just left with that second.
Okay, thank you.
Sure.